Okay, my dear students, welcome to our today's lecture. uh, Let me display the pages of the book before you, which we are going to consult today. Well, this is page number 590 from the book by Arfkan. And you have the copy of this, you have already the soft copy of this book with you. The next topic is the orthogonality. The orthogonality property of the Bessel's functions. Mind you that we are still studying the Bessel's function of first kind. I would suggest that you must consult the orthogonality property of Bessel's function from the book by Gupta, and you must consult pages. Let me give you the pages from Gupta, which will be helpful to prove the orthogonality property of the Bessel's function. Okay, this is the page 724. Page 724 from the book Mathematical Physics by Gupta. So you consult these pages and follow the orthogonality property of Bessel's function. Okay, after this, let me switch to the next topic. The next topic is the Newman functions, or we also call them the Bessel's function of the second kind, represented by n nu x. The Newman function is defined here by this equation 11.60. n nu x is equal to cos nu pi into j nu minus j minus nu as a function of x divided by sine nu pi. This is the Newman function for non-integral nu. N nu x clearly satisfies Bessel's equation, for it is a linear combination of two known solutions, j nu x and j minus nu x. You know that if the differential equation is homogeneous, then any linear combination of its two solutions also satisfy the differential equation, and that's why the Newman function as defined by equation 11.60 satisfy the Bessel's differential equation for non-integral value of nu. But if nu is integer, then you see that both the numerator and the denominator become 0. So the Newman function becomes indeterminate. However, for integral nu, that is nu is equal to n, equation 11.8 will apply and equation 11.60 becomes indeterminate. So what we have to do now to find the limiting value of the Newman function for integral, we will have to differentiate both the numerator and the denominator with respect to nu, and then put nu is equal to n. Now this step is done here in these three lines, but I would suggest you to consult my notes for the detailed discussion of this. So n nx will be determined by the L'Hospital's rule, that is, the limiting value is obtained by differentiating both the numerator and the denominator with respect to nu, and then putting nu is equal to n. And this is how we get this equation, that nx is 1 over pi partial derivative of j nu with respect to nu minus into minus 1 power n partial derivative of j minus nu with respect to nu, and then we put nu is equal to n. So the Newman function as defined by this equation can be shown to satisfy the Bessel's differential equation, and these steps can also be seen from my notes that the Newman function as defined above satisfy the Bessel's differential equation. And let me show you. Okay, I would suggest that you must consult my notes to prove that the Newman function or the Bessel's function of second kind satisfy the Bessel's differential equation. Now the question is that why we have defined Newman functions. The Bessel's function of first kind, that is represented by j, we know that there is a problem if nu is equal to an integral integer, then the second solution does not exist, and we have to find the second solution by some other method. But the Newman function are being defined here to cover comprehensively the solution of the Bessel's differential equation, irrespective of whether nu is an integer or nu is not an integer, as we have seen above. We have two defining equations. One holds for non-integral nu, and the other, after applying L'Hospital's rule, is used to cover the integral n. Okay, so that's it for the Newman functions, but as we call it, the Bessel's functions of second kind. Now mind you that the rest of the algebra of the Newman function, like the algebra of the Bessel's function of first kind represented by j, for example, the generating function, the recurrence relations, the orthogonality condition, the integral representation. Now all those properties, all that algebra also holds good for the Newman function. The reason being simply that the Newman function is a linear combination of j n and j minus n, so it should satisfy the Bessel's differential equation, and as such it should also satisfy all the algebra which we have already read about the Bessel's function of second kind. Okay, so if you are asked to prove a certain algebraic equation for Bessel's function of second kind, that is the Newman function, you can simply discuss that equation, that algebra for the Bessel's function of first kind, and then simply giving the reason that Newman functions are linear combinations of the Bessel's function of first kind, hence they also satisfy the algebra. Okay, the next step is the Hankel functions, and we also call them the Bessel's function of third kind. Okay, the Hankel functions are defined by equations 11.85 and 11.86 as a combination of the Bessel's function of first kind and the Bessel's function of second kind, making the Bessel's function of first kind as the real part and the Bessel's function of second kind as the imaginary part. So we have h nu 1 x is equal to j nu x plus iota n nu x, and we define the h nu 2 as h nu 2 x is equal to j nu x minus I n nu x. So we have two Hankel functions defined here. The first is called the Hankel function of first kind, and the second is called the Hankel function of second kind. Okay, now why we have defined Hankel functions? Because if we are not dealing with real variables, we are dealing with complex variables, then you know that our solution must contain both the real and imaginary parts. So here is the reason why we have defined Hankel functions like this. So Hankel functions, that is the Bessel's function of third kind, they also satisfy the entire algebra designed for the Bessel's function of first kind. Okay, so let me now jump to another type of the Bessel's function, that is the spherical Bessel function. So I'm jumping over to the spherical Bessel function. Let me see, where is this topic? Let me find this topic from this book, the Bessel's function. There. Okay, so this is the spherical Bessel function. Now sometimes we come across with equations of the fashion of equation 11.139. Now if we look at this equation carefully, we see that this is not essentially the Bessel's differential equation, because we have r square, fine, but the second term is not just r, it is 2r, and then we have this term over here. So this is not actually the Bessel's differential equation, but with a little bit of labor by changing the variables, the dependent and the independent variables, we can convert this equation into a Bessel's differential equation. Okay, so this is the transformation that we define r as a function of kr by zkr, and when we use this in our equation, equation 11.39, this transformation, and you can see all these steps done in my notes, and you will have to consult my notes for these steps which are not shown here in the book. But then with this transformation and after these steps, this equation takes this form. Now this form is quite similar to the Bessel's differential equation, because now we have r square d2z over dr square plus r dz by dr plus k square r square minus n plus half square into z is equal to 0. So here we have the a form of the Bessel's differential equation, and we see that this is the Bessel's differential equation of order n plus half. Okay, so the solution can be written for this particular equation through this equation using the Bessel's functions of first kind and the Bessel's differential equation, and we represent the spherical Bessel function as we have defined here by small alphabets. So small j n x is defined as pi over 2x under root j n plus half x. Similarly, small n nx. So this is the spherical Bessel function of first kind, and small nx is the Bessel's function spherical Bessel function of second kind. Then we have the spherical Bessel function of third kind, that is the Hankel functions. So these defining equations correlate the spherical Bessel function with the ordinary Bessel's function, and the reason I have attached with these definitions is because sometimes our equation, especially in spherical symmetrical problems, are not exactly Bessel's differential equation, but they can be converted into these Bessel's function, that is, as we did here, that equation 11.139 takes up the form of equation 11.140. So please go through all these steps from my notes to see this conversion. And so this is how the Bessel's functions, spherical Bessel's functions, are defined, and this factor pi over 2x under root is in fact the normalizing factor attached to these. So okay, so we have three, this is the fourth type of Bessel's functions, the spherical Bessel functions, which are used in physical problems where we have spherical symmetry present. Okay, now one of the direct applications of the spherical Bessel's function is given in a problem over here. Let me find this problem, this example, if I can find it now. Okay, I think I have skipped, so let me go back and find. Okay, so this is the example 11.7.1, that is particle in a sphere. So this in this problem we will use the spherical Bessel function. An illustration of the use of the spherical Bessel function is provided by the problem of a quantum mechanical particle in a sphere of radius a. Quantum theory requires that the wave function psi describing our particle should satisfy this equation and the boundary conditions. First boundary condition, that the wave function for r less than or equal to a remains finite, and the wave function at r is equal to a must be 0, because the particle is contained in a sphere. So I would also again suggest that you must go through my notes to see the discussion of the particle in a sphere and all these steps. There are several jumps here, but you can fill these jumps by consulting my notes and reach to this equation 11.173, which is the energy eigenvalues, the minimum energy of this quantum mechanical system in which a particle is contained in a sphere. Okay, so I think that's all as long as the Bessel's functions are concerned. So we have concluded our chapter in which we have discussed the solution of the Bessel's differential equation in much detail, because the Bessel's functions are very common in our physical problems. Okay, so take my notes from the photostat shop and go through these notes. The portion which I have discussed here, that portion must be seen. The rest of the portion you can skip because that is not very much important, but the portion I have covered from in my lectures is the important portion, and you must be able to answer any question from this. So that's all for today's lecture, in which we have concluded chapter number 11, that is the Bessel's functions. Okay, in our next lecture we will take up Legendre functions, which are the solution of the Legendre differential equation, and Legendre differential equation, the second most common differential equation in physical problems. Okay, thank you very much. So please, as I have suggested, go through all this book pages as well as the notes. Okay, thank you.